This is the brief on the damped wave equation and real-world wave behavior. So, ever wonder why the perfect waves you see in physics models don't quite match what happens in real life? It's all about energy loss. We're going to look at how mathematical models describe these perfect, idealized waves, and then how they adjust to accurately show what really goes on. Okay, first up, you've got the undamped wave. Think of this as your perfect physics textbook scenario. It's a standing wave that just oscillates forever, keeping the same height, the same amplitude. Because it's in a system that magically conserves all its energy. No friction, no drag, nothing. Second, we introduce the damped wave equation. And this is the game changer. It adds a crucial piece to the puzzle, a damping term. You can kind of think of this as a resistance force, a built-in brake that accounts for the wave losing energy to its surroundings, like the air. And finally, what does this actually look like? Well, it behaves just like things in the real world, say a guitar string after you pluck it. Because of that damping term, you can see the wave's amplitudes start to shrink. The whole oscillating shape gets smaller and smaller until the system just stops. It comes to rest. So in the end, the damped wave equation is what lets us model how real systems actually lose energy and eventually quiet down.